Let's talk about linear motion. Now, linear motion refers to situations that are moving in a straight line. And I know that sounds obvious, but we need to emphasize that, okay? So, what are the different types of situations you have? You could have a situation where it moves left and right. You could have a situation where it moves up and down. For example, you could have a height function that depends on t. Now, this height function, maybe it looks something like negative 16t squared, let's say plus 11t, something like that. Now, when you look at this equation over here, this equation does not look like a line, but this equation just gives the height. So in this case, maybe the ball is being thrown up into the air and then the ball comes back down. And this equation might give the equation of the height. So the object's moving is in a straight line, even though the function itself does not look like a line. Okay? So um, when we work with motion, a lot of times we care about the position, the velocity, and the acceleration. So you guys know that in the past, when we've looked at this situation, how do you get from position to velocity? You find the derivative. So you got to take the derivative with respect to t. How do you go from velocity to acceleration? You have to find the derivative with respect to t. So what I want to talk about now is I want to talk about going in the opposite direction. So if I want to go from acceleration to velocity, you need the anti-derivative. Okay? Same thing, if you want to go from velocity to position, you need the anti-derivative. So why don't we look at an example to see how this works? A car is traveling at a rate of 88 feet per second. So right away, when I see this, I can recognize that this is a velocity. How do I see that that's a velocity? The first thing they mention is that they mention it's a rate. And then the second thing they mention is that the units are unit of length over a unit of time. So actually, let me go back to my example up here. If we were to think about it in terms of units, you know, position is a unit of length. So maybe it's something like feet, or maybe it's something like meters. Then the velocity is a rate of change of position relative to time. So this could be like feet per second, or this could be meters per second. And then acceleration is the rate of change of the velocity per unit time. So this would be feet per second squared, or meters per second squared, because it's like meters per second, which is meters per second squared. So these are the different units we have for the different types of motion. Okay, so going back to this example over here, if I continue reading, it says, it says, a car is traveling at a rate of 88 feet per second when the brakes are applied. The car begins decelerating at a constant rate of 15 feet per second squared. So I hope you guys can see that when we look at the units over here, that's something involving acceleration. Okay, so let's take a look at part A. Part A says, how many seconds elapse before the car stops? So when I think about part A, the first thing I think about is the car stops. The velocity is equal to 0. So what I need to do is I really need to figure out what's the time t when the velocity is equal to 0. That's really what we're trying to figure out here. What I need to do then is I need to create a function for the velocity. In fact, I got to go and find my acceleration function, my velocity function, and my position function. So what's my acceleration function going to be? At this point, I want to mention to you all that they told us that this car is decelerating. Decelerating means, the rate of change of the velocity is negative. So my acceleration function is not going to be 15 feet per second squared because it's decelerating. It's going to be negative 15 per feet per second squared. Then if I want to find the velocity function is just going to be equal to the antiderivative of the acceleration function with respect to t, and that's going to be equal to the antiderivative of negative 15 dt. So when I calculate with that antiderivative, that's going to be negative 15t plus some constant. So the natural question to ask is, what is the value of this constant? And this is really an initial value problem. So they're telling me that a car is traveling at a rate of 88 feet per second, which is a velocity, when the brakes are applied. So we're going to say the following. We're going to say at t equal to 0, we apply the brakes. Okay? So now we have that initial value problem. That means that v of 0 is equal to 88. Well, truly 88 feet per second. So if I wanted to find the velocity function, I could simply solve for c. So I know that v of 0 is equal to negative 15 times 0 plus c, and that's going to be equal to 88. So this tells me that 0 plus c is equal to 88, which tells me that my c is equal to 88. So now I know my velocity function is v of t is equal to negative 15 t plus 88. All right. Now remember, I wanted to see when does the car stop. So all I need to do now is I need to set this velocity function I just found equal to 0 and solve for t. So when I do that, I'm going to get the following. I'm going to get 0 is equal to negative 15t plus 88. That means 15t is equal to 88, which means t is equal to 88 over 15 seconds. And that's my answer for part A. All right. Let's take a look at part B now. Part B says, how far does the car travel during that time? So when you see how far, we're really looking for a position type thing. So when I look at this particular question is just asking me what is the position after 88 over 15 seconds? This is true because we know from the moment we apply the brakes, 88 over 15 seconds pass before the car finally stops. So we want to know what's the position after that amount of time, and that will give us the stopping distance. So we're just going to simply substitute this 88 over 15 into our position function. The problem, though, is we don't have our position function yet. So what we're going to do is we're going to take our velocity function and we're going to find the antiderivative. So our position function is going to be equal to the antiderivative of the velocity with respect to t. And that just means you're finding the antiderivative of negative 15t plus 88. Okay? You always want to put the t at the end. The antiderivative of this, well, I could break this up into different pieces if I wanted to. I can find the antiderivative of the first term, that's going to be negative 15t squared divided by 2. I can find the antiderivative of the second term, that's going to be plus 88t. And then we're going to have a plus c. Now, this c should be the initial position. So let me label that as the initial position. Okay? But that initial position is going to be 0. You know, this is the point at which we start applying the brakes. Okay? So I'm going to set that equal to 0 because that's going to be the moment I start measuring the stopping distance. So long story short, our position function is going to be equal to negative 15t squared over 2 plus 88t. And then the distance that I'm looking for is going to be s of 88 over 15, which is going to be negative 15 times 88 over 15 squared plus 88 times 88 over 15. And I'll let you pop that into your calculator at home. Just make sure that you include your units at the end. Our units for position are the same as our units for distance, which is a unit of length. In this case, it's going to be feet. So I'm going to highlight this. And that's it for this video, folks. Take care.